Well, hello everyone. Welcome to our first webinar of 2021. My name is Lloyd Do. I'm a member of the NSF Center for Integrated Catalysis. So it is my distinct pleasure today to welcome Alex Miller from the University of North Carolina at Chapel Hill. Alex did his undergraduate work at the University of Chicago, where he worked with Greg Hillhouse on some beautiful nickel chemistry. He then went on to move to Caltech, working with John Burkall and Jay Labinger on some chemistry involving emissive copper complexes and coupling and monoxide. And he received his PhD in 2011. He then moved to the University of Chicago, where he worked with Karen Goldberg and Jim Mayer as the Dreyfus Environmental Chemistry Postdoctoral Fellow. He did a variety of things there, including studying formic acid disproportionation to methanol, cleavage of CO bonds using iridium complexes. Alex then, from starting in 2012, moved to the University of North Carolina, where he currently is as an assistant professor. He was then promoted to associate professor in 2018. So I actually met Alex when he first visited MIT for a brief time when I was a graduate student in the lab, but he actually left the Burkall group by the time I joined, so I didn't get to experience have the privilege of having Alex as a lab mate. However, I've followed his group's work at UNC very closely, and I've always been inspired by a lot of the beautiful work that has come out of this group. So Alex's group works on developing catalysts for sustainable production of fuels and chemical building blocks, particularly with an emphasis on understanding fundamental mechanistic details of those reactions. And so just to give you an idea of how productive Alex has been in just a couple of years at UNC, his group has so far published over 40 papers. Many of them are in JACS and other high impact journals. He has given over 40 invited talks, so he's widely recognized in the field and highly respected in the organometallic chemistry community. So not surprisingly, Alex's list of awards is quite extensive, so I'll just give you a few. In 2013, he was named Forbes 30 under 30 for investigators who are investigating energy-related issues. In 2016, he received the NSF Career Award, as well as the Sloan Research Fellowship. In 2017, he was the Organometallics Distinguished Author, or received the Organometallics Distinguished Author Award. In 2018, he was the Chemical Communications Emerging Investigator Lectureship, or gave the lectureship. And in 2019 and 2020, he became the advisory board for organometallics and ChemCom. So without further delay, let me once again welcome Alex to give us a tutorial on surface attachment strategies in catalysis.
Awesome. Thanks, Lloyd. That's a too kind introduction. Really, it's a pleasure to be here, and thank you all for coming. I'm going to talk about surface attachment strategies. These are sometimes called anchoring groups, which is why I've got pictures of various marine anchors on my title slide. It's not an area of my own expertise, as you'll see as we go through, but something I'm learning more about and am excited to share what I know about. So these webinars are put on by the NSF Center for Integrated Catalysis, and one of the big overarching goals of the center is to utilize multiple catalysts together in the same vessel, performing multiple steps of reaction sequences involving several catalysts. And to do that requires, in most cases, both temporal control and spatial control. We have to control when each catalyst is operating, and oftentimes where in space they are, so that they don't interact with each other in bad ways. So that sort of inspired the topic for today's webinar, which is to focus on one of the key tools for spatial control, which is methods for attaching catalysts to surfaces and materials. So I'll just start with my own sort of, traditional view of how to classify different types of catalysts. And I think if you go look at most textbooks, it'll say you can either have a homogeneous catalyst or a heterogeneous catalyst. And so I have just a couple, somewhat randomly chosen examples on this slide of sort of a classical view of a homogeneous catalyst, some well-defined transition metal complex that can be synthesized, isolated, and then dissolved in solution. And the reactions it carries out are in a homogeneous solution with a dissolved catalyst. And then heterogeneous catalysts are typically thought of as materials that are insoluble in the reaction phase and often have heterogeneity in their active sites as well. So, in this example, there's a small cluster of platinum atoms, but there's also single platinum sites that are dispersed in the support material. And you might have edges or corners or vertices that are more active than the planar material itself. So that's the maybe traditional view. I think that there's lots of examples of systems that sort of challenge that view. And what we'll talk about today, I think, fall into that category to some degree. But we try to make these webinars interactive on several levels. And so I thought I'd start the talk thinking about some of these sort of classification challenges. So here's the same catalyst structure I showed you on the prior slide. But Himeda and Onishi and coworkers are now using this not in solution, but as a solid. They synthesize the catalyst and they put it on the bottom of a reactor. And they allow it to react with two gas phase reactants, CO2 and hydrogen, and methanol is formed. So the reactor looks like this. It's a pressure vessel, solid catalyst stirred with CO2 and hydrogen gas. And they looked at this monomeric iridium complex as its solid powder, as well as this dinuclear complex as its solid powder. And what they observed is that the dinuclear catalyst in the solid lines produces a fair amount of methanol, certainly relatively speaking to the monometallic catalyst, which is essentially inactive. And this reaction is more efficient in this gas phase setup than it is in a homogeneous solution. So I'm going to have Julio open a poll, and I'll just sort of get everyone's opinion on, how to classify this reaction. Is it a homogeneous catalyst, a heterogeneous catalyst, a molecular catalyst, or a supported catalyst? All right, so about 2/3 said heterogeneous, about a third or a quarter, 27% said molecular, and 12% said supported. Nobody said homogeneous, which I think is a good start. I would say that there's not a single right answer to this. It's intentionally chosen to be sort of an unusual case. And for me, I'd say this is a heterogeneous reaction because it has multiple phases, solid, and gas phase, and a liquid product. But it's also probably a molecular catalyst in the sense that it's a well-defined molecule that was placed in the reactor. It's not a sort of periodic inorganic material or something like this. So I think this also serves a role in sort of adding some subtlety to the distinctions we have. It's not just homogeneous versus heterogeneous, but the molecular versus materials nature of the catalyst, I think, is a really important classification as well. So I'll give a couple other examples of blurring lines between catalyst classes. So this is an example I love because of my own background in molecular catalysis and frequent concerns that a molecular catalyst is simply decomposing into a highly active nanoparticle or metallic catalyst. Here's an example of a palladium nanoparticle that's used as the catalyst for a Suzuki cross-coupling reaction. And mechanistic studies showed that the active catalyst itself, after an oxidative insertion or oxidative addition of the aryl halide, undergoes an etching process to generate a discrete, well-defined molecular palladium species that undergoes the transmetallation and reductive elimination steps. So what appeared to be a heterogeneous catalyst in the classical sense of, palladium metal nanoparticles actually, in fact, is leaching small, well-defined, homogeneous molecular catalysts that can either continue on a molecular cycle or reform nanoparticles, and you've got this very dynamic system going on. So I think that's a really fascinating example that also sort of blurs the line between these catalyst classes. Another sort of edge case, so to speak, is this silica surface that I have depicted here, where an iridium catalyst, not too different from the one I showed earlier, has been attached through a phenyl linker to the silica surface and studied as a supported molecular catalyst or single site catalyst. This is the type of catalyst that'll be in focus today. It has some of the properties of a well-defined molecular catalyst. It's got only one type of iridium center here with all the same ligands around it. It was synthesized and isolated before it was attached to the metal, to the material support, the silica support. But it has a lot of the features of a heterogeneous catalyst in that it's in the end, you have an insoluble material that is catalytically active. So why surface supported catalysis? What's worth spending an afternoon, an hour of your day talking about here? The argument for a surface supported molecular catalyst is that you might be able to get the best of both worlds. You can easily separate your catalyst from the reaction products like a heterogeneous catalyst, or avoid catalyst-catalyst interactions if you have a multi-catalyst system, which is also possible in heterogeneous systems. You can, for the particular case of electrocatalysis, ensure that all of your catalyst material is in the reaction diffusion layer close to the electrode, which is a challenge in homogeneous electrocatalysis. But with all those heterogeneous benefits, you also may get the high activity, high selectivity that comes with a single well-defined catalyst in homogeneous catalysis. So as I mentioned, this isn't really my area of deep expertise. I come from a background of molecular catalyst development, and from that perspective, I'm quite interested in retaining the things that I love about molecular catalysis, including being able to understand the mechanisms on surfaces, but getting some of the benefits of heterogeneous catalysis, or being able to support multiple different types of catalysts on a surface. I have dabbled in the art a little bit. My group has worked on and is working on some projects that involve supported catalysts, often in collaboration with chemists who have more of a materials background and can guide us and help us and work together. And I've been involved in centers like the CIC that where this is a priority. And so that's been sort of where I've sort of been a fly on the wall collecting insight. So I'll try to share what I know from those interactions. And I think it's also worth saying that, in an hour, one can only really scratch the surface of, what's out there in terms of supported catalysis. So this is going to be, a goal here is to be broad and cover concepts and approaches more so than to be comprehensive in any way. Okay, so with that said, I'm going to organize the presentation today based on sort of a synthetic approach. And so the first part will be about how to functionalize a catalyst to enable its attachment to surfaces. And then the second part is going to be how to functionalize a surface to enable it to be attached to by a catalyst. And you'll see the sort of differences in approach as we go through. And the other thing you'll see is that the bonding picture is pretty diverse here. There's a lot of different chemistry involved, and they range from sort of non-covalent interactions that seem fairly weak to strong covalent bonds and more dative type interactions. So that's true for both parts. And also true for both parts is that you can sort of divide supported catalysis into the camps of sort of thermal organometallic catalysis, where your support is really there to take the catalyst out of the solution phase and into the solid phase and help with separations and recycling and things like that. And the electrochemical catalysis, where the support is essential because it's also your electrode. It's delivering or receiving electrons during the reaction. So that's a major divider in how people approach this chemistry, and one could organize a talk that way, and I just chose to sort of choose the other route with synthetic bases. Okay, so part one, I'll talk a bit about how to functionalize catalysts to put them on the surface, and this just sort of gives you a big roadmap of where we're going, all the different kinds of linkages that are out there, or at least a smattering of them, and where they lie on the continuum of sort of covalent to non-covalent bonding. So I'll be about one slide per technique, and I'll try to weigh the pros and cons a little bit, and they're not presented in any particular order other than what struck my fancy as I put the slides together. So the reason I'm starting with transition metal directly binding to silica is that may be the oldest sort of well-defined single site support chemistry that's out there, and it's in some ways very general and in some ways very narrow. Many different transition metal alkyl complexes can be synthesized, and many of these are amenable to attachment to silica surfaces. This undergoes a sort of protonolysis reaction that releases the alkane corresponding to one of these alkyl ligands, and you form a direct linkage between a transition metal catalyst and a silica surface. So these are readily synthesized. You can see just a couple examples involving an early metal and a later metal that take advantage of this sort of alkyl protonolysis to form a metal oxygen bond. And they've been studied in great detail for their sort of thermal catalysis on silica. The drawback, or potential drawback, is that you need this ligand that's now directly bound to the metal to be amenable to the chemistry that you're interested in. So if your catalyst tolerates an alkoxide ligand in solution, it's reasonable to guess that a linkage like this silicon oxygen bond might be a suitable ligand in a surface catalysis as well. But there's other systems that, once you change the bonding by forming this metal oxygen bond, you may shut down whatever homogeneous catalysis you had seen previously. So it's clearly very directly linked to the chemistry of the transition metal center. The stability varies a lot as well, depending on the sort of strength of these metal oxygen bonds. So early metals with their stronger metal oxygen bonds tend to survive longer in these sorts of surfaces than later metals. Another really prevalent technique is to use various oxyacids, so especially carboxylates or phosphonic acid derivatives are commonly used, as well as sort of silane derivatives or silanol derivatives. These typically are found binding to metal oxides and of a wider variety. So silica included, but also titanium dioxide or tin oxide or nickel oxide. An advantage of this, or one of the key reasons to choose an attachment like this, is that it's quite amenable to peripheral attachment on your ligand. So this ruthenium complex shown here shows a pyridine ligand where the pair position can either have a carboxylic acid or a phosphonic acid or a hydroxamic acid. And that means that when you link the complex to the surface, the linkage is far away from the metal. So you're not going to perturb the d orbital energies or the metal ligand binding as much as if you have a direct metal to metal oxide linkage as in the prior slide. Oftentimes in organic solvents, these linkages can be very strong and stable for days or weeks. In water, stability is the big knock on oxyacid linkers. So an example is that carboxylates will bind to something like titanium dioxide pretty well at pH 1, but as the pH goes above about 4, you get hydrolysis and desorption from the surface. Phosphonic acid derivatives bind better about to neutral pH, and hydroxamic acids and silanes tend to have better stability under basic conditions. So these silicon linkers, there's a lot of different precursors you can use. One example from which I pulled this table looks at silatranes that are convenient because you have a quite stable silane reagent that you can that's relatively bench stable, but you can still form a robust linkage to the surface. Another sort of widely used approach is to use diazonium salts. And this was first looked at especially on carbon materials. So a diazonium would be installed on the periphery of a transition metal complex or catalyst, and then it would be grafted onto a carbon material, usually electrochemically. And so it turns out this is more general than I knew, certainly more general than just carbon. This works for some metallic electrodes as well as semiconductors and metal oxides. And the general approach is that you undergo some oxidation reaction, usually of an amine in your backbone to make a diazo group. And then the diazonium undergoes an electrochemical reduction to generate an aryl radical, in this case, that then forms a bond to the metal oxide surface. So they tend to form pretty strong covalent bonds and have quite good stability. And this versatility in the surface chemistry is good. One limitation is the need for an electroactive surface. So if you need to do an electrochemical reduction to trigger the surface attachment, you need to have a conductive material support. And then there's some compatibility challenges potentially, that the conditions, for example, to form a diazonium may not always be compatible with the catalyst you're interested in. You may decompose the catalyst, or you might have concerns about this safety or stability involving these relatively high energy intermediates. Another classic sort of attachment approach involves thiol binding to gold. This is, again, one of these classical surface modification approaches. You may have heard of self-assembled monolayers on gold, or SAMs, and that's been used as an approach to attach catalysts. One of my favorite examples comes from Coleman and Chidsey, who built this just extraordinary model of cytochrome C oxidase that has an iron center and a copper center and a phenol to model a tyrosine. And then they looked at different linkers attaching it to gold and varied the distance and the electronic coupling to this electrode, and investigated how that affected the oxidase reactivity. So, advantages of this is that there's so many decades of research into these self-assembled monolayers that you can sort of, if you have the right alkanes with the right length, you can have a good idea of what the surface structure looks like. And you're quite remote from the catalyst center again. And it's a relatively rare strategy that's amenable to a bare metal surface like gold. rather than metal oxides. A relatively recent development is that N-heterocyclic carbenes are also quite good anchoring groups for gold. And so these offer very different structures, different coverage patterns. And so that's been an area of recent interest in this field. Okay, I think the last of the sort of catalyst modifications that I'll introduce is those involving non-covalent interactions, most commonly with pi-pi stacking interactions. And the irony in having this at the end of this section is that this is maybe the only case where there are some catalysts that need no modification at all to undergo a non-covalent interaction with an electrode. So some catalysts like porphyrins or phthalocyanins have aromatic ligands that will form pi stacking interactions with carbon electrodes spontaneously. Other times you need to install an aromatic group like a pyrene at the periphery of a catalyst to engage in these non-covalent interactions. Generally, these have been done on graphenes or carbon nanotubes as the materials of support. More recently, there have been efforts that sort of modify the surface to enable these attachments non-covalently, such as putting a pyrene group on the electrode surface or on a material surface, and then having another pyrene group on the catalyst and allowing them to come together. Or in this example, that's from Jenny Yang's group. In this example from Javier Concepcion's group, using long chain alkanes to have sort of hydrophobic interactions that put the catalyst on the surface of a metal oxide. Water is maybe the solvent where this is most commonly seen, and a lot of times that's because the aromatic containing catalysts are not soluble in water, and so desorption is mitigated by the insolubility of the catalyst. But these approaches, in theory, can be used in a range of solvents so long as they're not forcing desorption by competing pi-pi interactions. Okay, so I'll switch gears now, and you know that slide sort of foretold what I'll talk about next, which is how to functionalize a material to achieve an anchoring group that is strong and robust and fulfills the needs of the chemistry. So one example, also built on carbon, takes advantage of the sort of imperfections, if you will, on graphitic materials. This is work pioneered by Yogi Surendranath and his group that took advantage of the presence of these dione units in graphite materials and built catalysts that have these diaminobenzene groups, and they undergo a condensation to form these pyrazine units. And that allows for a very direct attachment of the catalyst to the graphite electrode. And considering the prevalence of carbon materials in electrochemistry, it's quite valuable for those studies. This is maybe a unique linkage in what I'll present today, because it shares an aromatic system with the electrode material itself. And that has quite striking effects on how the catalyst behaves, because the orbitals are sort of delocalized into the electrode material itself. So that's been, I think, an interesting field to watch develop because of the electronic structure considerations. I'll tell one very short story that I was involved with rather than only highlighting the work of others. And that involves trying to circumvent some of the stability challenges that come with phosphonate anchors. So I was involved in an Energy Frontier Research Center where phosphonate anchors for catalysts and light absorbing dyes like rubipi were the dominant strategy for surface attachment. and stabilization was a huge challenge because we wanted to work in water, and ideally water at pH 7 or even more basic. And so one of the many strategies that have been taken to try to enhance the stability was to go from phosphonate to silane linkages. The problem is that the silanes tend to be pretty reactive. Synthesizing the catalyst with pendant silanes was often problematic, and you'd have hydrolysis or side reactions, or they wouldn't be compatible with the catalyst. And so the approach that was taken was to instead functionalize the surface with an azide group. So um, prepare a relatively simple azide-containing silane that could be rapidly synthesized and utilized before it hydrolyzes, and form a functionalized surface where you have strong anchoring groups in the form of these silanes, and then a new functional group in the form of the azide. And then a catalyst was prepared that has two alkynes, and you can see where this is going towards a click reaction where copper catalyzed cycloaddition was carried out to form these triazoles. So now you have a strong linkage to the surface, a covalent linkage to your catalyst, and a controlled reaction. So this is representative of, I think, all of the examples in this part of the talk that we don't just need to do surface functionalization chemistry, installing azide groups. We also need to do what we did in the first part and functionalize the catalyst as well. But in this case, it's a functional group that would not attach to a surface on its own. It's designed to pair with this with azide that has been decorated on the surface. So I'll do one more poll, and I'll have Julio launch it. And this again has no right answer per se, but is just to provoke some of your thinking and see how people would approach this. You know, what spectroscopic tools, looking at these intermediates and products, would you use to look at these reactions? What would be the most valuable? All right, and the answer is evenly split between everything. That's totally fine because I think that you could use all of these, and you know, one of my strong beliefs is that the more spectroscopy and the more characterization tools you have at your disposal, the more you're going to learn, and the more conclusive your picture of the surface will be. So IR was the winner there by a hair, I guess, and that was the one I was going to highlight. In part because we have these azide linkages, and then there's also alkynes. So those are two nice, strongly absorbing IR handles, and the triazole even has some signatures as well. But what ended up being really helpful was to look at the IR spectra of the surface before and after this silanization, and you could see the azide stretch appear. And then after addition of the ruthenium complex, you could watch the azide stretch disappear. And you could also look for alkyne to know if there was any unreacted ruthenium complex left and didn't undergo the click reaction and was just sort of physisorbed to the material. So there usually was a little bit of azide left over, just based on the amount of ruthenium that we could pack. These are a lot bigger molecules than these azidosilane units. So we think that sterically, not all of the azides were chemically accessible. Cyclic voltammetry is also super useful after we got to the product, because this has well-defined redox events that you can use to learn how much ruthenium is on the surface, for example. Okay, so what happened in these studies? The outcome was indeed that the stability was much higher than prior systems that had been looked at in the center. And so you can see, just soaking these slides in water at different pHs, At pH 1 and pH 7, the stability is basically, we don't see any loss in surface binding over 24 hours and only about 10 or 15% desorption all the way up to pH 12. If you want to compare that to the same Rubipi-based molecule with phosphonate linkages, that is almost entirely desorbed, even at pH 7 water over 24 hours. So a big difference in stability coming out of this. So here's a related example that doesn't use azides or click chemistry, but uses the same approach of taking a silane precursor to functionalize a metal oxide surface, in this case, a mesoporous film of nanoparticles of TiO2. So this is a vinyl silane, and it forms a vinyl decorated surface. And then this was subjected to a reductive electropolymerization. So a vinyl containing Rubipi unit was brought into the reaction mixture, and reductively you form a carbon-centered radical on these olefins that kicks off a polymerization event, and you get a network of ruthenium complexes anchored to the surface by these silicon oxygen linkages. So there's pros and cons to this. The advantage, especially considering this is a light absorbing dye, and that the goal of this work was to sensitize the transparent TiO2 to visible light, is that you get a large number of ruthenium complexes near the surface. This is not a perfect monolayer by any means, and you get sort of a polymer network of complexes that is going to increase the light absorption profile. The cons are that it's not a very well-defined surface. So being able to, for example, get substrates to, some of these ruthenium complexes may be harder than one would like. So there's trade-offs in this approach versus the azide click chemistry on the prior slide. Okay, so those are the specific examples I wanted to share. I wanted to finish before we go to breakout rooms with a few thoughts about design principles. So, if you come into my office and want to talk about how to support your catalyst, these are the kinds of questions that we'll talk about. So my advice is to always consider your application first. What's the reaction you want to run? What are the conditions of it? Is it a thermal reaction or an electrocatalytic reaction or a photocatalytic reaction? And that has big implications in what your support material should be. If it's an electrocatalytic reaction, you need a conductive support material. You need to worry about how well your linker is going to couple to the electrode surface. Are you going to have slow or fast electron transfer between the electrode surface and the attached catalyst? If you're running a photocatalytic reaction, you should probably have a transparent support material so that the light isn't reflected away from the catalyst or the chromophore. And you're going to need to bind enough catalyst to absorb light. I alluded to that on the prior slide. And that may mean that you can't use a planar material, but you need a high surface area material to absorb enough catalyst to absorb the light. Considering reaction mechanism is important. And I would argue, I'll give just two examples of where that can play an important role. One is if you have a bimolecular reaction. So for example, in some water oxidation catalysts, two ruthenium oxos from two different catalysts need to come together to form an oxygen-oxygen bond. But if you anchor your catalyst to the surface, that may not be possible to geometrically get to the right configuration to form the OO bond. So you may need a long flexible linker to enable the two catalysts to find each other. Ligand dissociation steps can be problematic as well. For example, if you have your linker attached to the periphery of a ligand that dissociates during the catalytic cycle, that could be a problem from a stability perspective. I mentioned solvent a couple times here, and I think that makes a big difference in the choice of linkers and materials. And I would say that the synthesis matters a lot too, in terms of what a catalyst will tolerate as it's being functionalized for anchoring to a surface, and what kinds of functional groups are going to be compatible with the catalytic reaction later on. So those are sort of some thoughts that might help guide people to as they design systems like this. So I have a few more slides, but I wanted to send people to breakout rooms and then come back and talk a little bit more and on the topic, particularly of sort of challenges. What can go wrong with supporting a catalyst on a surface? And so I'd love that to be the topic of discussion in the breakout rooms, to think about what are possible pitfalls or things to watch out for. And if people have experience in this field, what they've had success with in terms of overcoming said challenges. Does anybody want to share any discussion from the breakout room or challenges that that came up? And then maybe I'll solicit a few inputs or suggestions from the crowd, and then I can I'll show the slides that I have prepared on what I've thought of as potential challenges.
So Alex, we have something, but we are kind of cheating since I was in the breakout room with Christine and Henry. So I'll let other people go first.
Okay. And I would say, yeah, you can either raise your hand, I can see the participants list right now, or you can just unmute yourself and speak up.
So I can talk about, I have a good discussion with Alex in Karen's lab, and one thing we kind of feel like is sometimes the recipe changes if you're using different ligand, functionalize it. And so the safe way to do is to using a like commercial ligand, as Alex said, and the functionalize on the surface. But sometimes doing this itself is hard to claim a victory. So you have to using some more precious ligand that you made by yourself. But when you made those selves, they are so precious, sometimes make the it make much longer to get there. And that is the kind of dilemma when you're thinking about whether you should functionalize or not. Yeah.
Yeah, I think that's very wise. Counting the steps in the synthesis, how many are likely to work well or not, and what's the balance between a really fancy ligand versus trying something simple that might not work quite as well. Other thoughts, challenges that might be prevalent in this field?
Harry, go ahead and ask or like formulate your concern, I guess.
Yeah, it was kind of a discussion, but I was thinking that the mechanism in supporting catalyst, processes must become challenging, and I don't have a ton of experience with it, but yeah, I guess I was wondering if, mechanistic studies on a very similar discrete version of the catalyst can kind of easily be carried over to a supported version. And, in most cases, can you reliably expect your catalyst to pretty much go through the same catalytic cycle? Or I'm sure it gets challenging. And also we talked about how it's difficult to do mechanistic studies directly on a material or a supported catalyst.
Yeah, those are great points and good discussion. I think, one of the challenges is even how to compare rates or mechanisms between a molecular homogeneous species and a heterogeneous species, right? One is often, is going to be mass transport limited in some ways. There's sort of fundamental challenges in how to even compare apples and oranges, right? So, and then there's sort of challenges in how to, probe mechanism at the surface as well. So I think it is a challenge. One area where I've seen some of this is in electrocatalysis, where there's there's an interesting situation because you can only do electrocatalysis at the surface. Or by definition, the electrode needs to move an electron to or from a catalyst. So in homogeneous solution, it happens because diffusion brings a molecular catalyst close enough to the surface where electron transfer can happen. But in space, you're sort of constrained in the same region as if it was attached, right? And then then you're stuck in that reaction diffusion layer. So there are methods to obtain kinetic insight into molecular electrocatalysts in homogeneous solution that take into account the rates of diffusion and the kinetics of electron transfer and whatnot. And you can sort of back out the rate constant of a chemical step or what the turnover frequency of the molecular catalyst is. And that's done very commonly. And then you can compare that to sort of the directly observed rate of catalysis of a supported catalyst on an electrode. And I'd say I've been surprised by how well those numbers can agree when you have a well-defined species in solution versus on a surface. They certainly don't always agree and things can go wrong, but that's a case where there are tools from the electroanalytical sort of mechanistic toolbox that enable that comparison. And in the favorable cases, the rate constants are very similar and the turnover frequencies are very similar.
So Alex, because I work on electrochemistry, I just want to add on your comments. I assume you're referring, say, the photo wave analysis, something like that. One, in my perspective, because I work on that, is electrical measurement is counting electrons is much more sensitive than measuring vibration intensity. That's part of the reason why EChem can do it. But an ironic part of that is electrochemistry is more even using I'm not trying to say promise that's can solve all the problem, partly because usually it's much more accurate to determine turnover frequency for molecular electric catalyst when the catalyst is good. When the catalyst is not that good with slow turnover frequency, it's sometimes that's what you really want to solve. Sometimes it's not that accurate. But I agree, it's at least better than some other alternative strategies. Yeah.
Well, that's a great point. Excellent. Any other?
Alex, can I just make a comment?
Yeah, go for it.
You trained your student well. He brought up like some very nice points. I think you paid him to ask the questions.
Yeah, got the Carolina.
I'm pretty sure you didn't, but I like we got cut out, and I was going to also give the example. Probably some of the best characterized surface catalysts are what are known as surface organometallic catalysts. They were started being developed by Basset, and now it's like Cooperet at ETH Zurich. I don't know how many of you are aware of those. And they are like truly, I mean, organometallic chemistry married with well-characterized surfaces. But those are relatively rare. And then as you move a little bit further away, it becomes more complicated.
Yeah, I tried to sort of pull those into maybe my first example that had sort of the hydrolysis or protonolysis of the metal alkyl bonds. But I probably didn't do enough justice to how important Basset and Couperet's contributions have been. The one thing I'd say that goes back to some of the discussions that were going on in my breakout room and some of what we've heard here is that what's beautiful about those silica supported systems, the organometallic systems, is that you can do that on sort of large surfaces that are pretty well defined, or you can make little nanoparticles, little clusters of silicon oxides that end up being soluble. And so, for me, one of the beautiful things about that chemistry is that you can, again, do pretty nice, characterization comparisons with sort of homogenized and homogeneous little fragments of silica with the organometallic fragment on there, as well as and try to extrapolate that to the surfaces that are harder to characterize. All right, let me share my screen one more time. Everybody see that? Okay. The challenges that I came up with, just to finish off the discussion, number one was characterization. We heard that alluded to. And there's a ton of techniques, but none of them are, maybe as definitive as an X-ray crystal structure of a small molecule, or a molecular catalyst, or high resolution solution NMR spectrum. So I won't go into detail of all of these, but I think what I'll emphasize is that we talked about this. Model complexes are valuable to make comparisons when you can. You can sort of intentionally choose to incorporate functional groups or elements that provide valuable handles. So a functional group example would be like that azide linkage, or an ester that has a CO stretch that you could look at in an IR spectrum. An element example would be something that has an XPS handle, that you can sort of do elemental ratios to see if, say, your phosphorus to transition metal ratio is the same in solution as it was after you supported it on a surface. And then, like any good characterization, using lots of techniques together to do the best you can to get a picture of the surface is a good approach. The other challenge is stability. And this can be stability defined a lot of ways. You can have side reactions where the ligands decompose because of the Lewis acidity of a metal support or something. But most common is probably desorption in the examples I gave today. And there's a bunch of different strategies, and I alluded to a lot of the stability challenges during the talk. One of my favorites is what's called the mummy strategy, where you attach a catalyst to a surface and then you use atomic layer deposition to put more inorganic material on top of it until it's completely buried. And in this case, Tom Meyer's group also added a molecular catalyst as a second component on top of that. So you had a sort of a redox relay here that wasn't making any bonds, and then a catalyst that was doing, say, water oxidation on top of that. And so, these were both prone to desorption in neutral water, but after putting these TiO2 or alumina overlayers using ALD, they have much better stability. So that's kind of a neat approach. And then I think the other challenge that sort of goes back to what I was talking about in the beginning of how do you get multiple catalysts onto the surface and avoid interactions would be patterning. And there's many different ways to pattern surfaces to have different chemistry. And so I won't go into it at all, but there are some that are really simple. Like if you have two catalysts that have phosphonate anchors, you could have a 1-to-1 mixture in solution and just dip a metal oxide slide in and see how they load. Or you can prepare different patterns where you might have a metallic surface and then a metal oxide surface, or even something like this dip pen nanolithography that Merkin's group introduced, where you have a solution of your catalyst on an AFM tip, and then you write like a pen, lines or dots to form regions of a substrate that are patterned. So that's an area that is I think not so explored as some other places I've talked about today for catalysts, but is certainly an area of a lot of interest for other research areas. Okay, that's what I have planned. On Twitter, I promised that I'd try to work a sea shanty into my talk, and so I thought I'd end with this one that I found that seemed appropriate for the world we're living in. The times are hard and the wages are low. Amelia, where are you bound to? So we've been talking about surface-bound catalysts, so it seemed like a good a good one to end with. So thanks for coming, and thanks for the good conversation.
Thank you, Alex.